Hi everyone, my name is John Wamburu. I am a PhD student at the University of Massachusetts Amherst. Today I'll be talking to you about our work titled Ride Substitution Using Electric Bike Sharing, Feasibility, Cost, and Carbon Analysis. I will start by looking at the background and the problem that we're trying to solve. And the first observation that we make here is that ride sharing has risen in popularity in the recent past. This is mainly due to its convenience. Now, originally, ride sharing came with the promise of reduced traffic and reduced carbon emissions by reducing our reliance on privately owned cars. However, it has actually resulted in increased traffic. And research has also shown that ride sharing is up to 47% more carbon intensive than personal car trips. And this is mainly due to dead miles driven while picking passengers. At the same time, another form of ride sharing that has risen in popularity in the recent past is bike sharing, and particularly electric bike sharing. Now, an electric bike is a bike that provides pedal assist to the user using an inbuilt motor and battery. This makes biking easy and ideal for long rides and rides that go uphill. Now, since most taxi trips are short, as we will see in the analysis that follows, they can easily be replaced or substituted with either an electric or regular bike, and this could potentially reduce carbon emission. With these observations, we ask the question, what are the costs and carbon benefits of encouraging more bike sharing as a substitute for shorter ride sharing car trips? And what is the feasibility of such an approach? Now, to answer this question, we use three main data sets. The first one is the city bike data set from the city of New York, which consists of about 19 million trips taken in the 1 year period between July and June 2018 to 2019. These trips were taken by about 18,000 bikes spread across 941 stations. We also use about 354 million taxi trips taken during the same time period by about 100,000 cars. We start our analysis by looking at how feasible it is to substitute a taxi trip with a bike one. And to do so, we look at three main things. First one is distance. Second is pickup and drop off locations and the convenience of the trip. Looking at the distance, we find that the median taxi trip is actually quite short, only about 2.7 kilometers. And this can easily be substituted and taken with a regular or electric bike. We also find that up to 70% of all taxi trips are within 200 meters of an existing bike station. This represents a walkable distance to which a user can walk instead of hailing a car. Finally, looking at convenience, we find that short trips are actually faster while using a bike than using a car. And this presents an interesting alternative for users in some cases. In addition to looking at the feasibility of trip substitution, we also look at which specific trips are eligible for substitution. And here we analyze conditions that are suitable for and those that are not for taking a bike ride instead of a car ride. We begin by looking at the effect of weather on ridership, specifically bike ridership in the first graph. And we find that undesirable weather such as rain and snow, as expected, leads to lower bike demand. This is in contrast to taxi rides, which see a higher peak demand during this undesirable weather days. And also there is a higher demand of car trips at night than for bike trips. And this is also expected because you would prefer to take a car trip instead of a bike one at night. We also look at the effect of the different days during which rides are taken, specifically working days versus holiday days. And we find that for bike trips, there is lower peak demand on holidays. This is mostly because people are not going into work and therefore not using bikes during the peak periods, but there is generally higher demand during the day or in the course of the day, which represent more leisurely trips taken during holidays. This is the same for taxi trips, which see a lower demand during peak periods on holidays as opposed to working days. And while sampling trips to substitute from the taxi dataset into the bike dataset, we stay conscious of these constraints, and we only sample trips that are very likely to be eligible for substitution based on the conditions during which that trip was taken. Now, looking at the actual ride substitution to determine which taxi trips should be replaced with bike ones, we propose a linear optimization framework whose goal is to minimize the number of required bikes while ensuring that the aggregate trip demand, which is made up of both the bike trip demand and the substituted taxi trips, is fully met. We also ensure that shorter rides are taken using electric bikes, longer trips are taken using, shorter rides are taken using regular bikes, while longer rides are taken using electric bikes, and medium distance trips are taken using either type of bike, depending on whichever is available at the start of the trip. Now we'll look at the formulation of our linear optimization framework. And before we do that, we'll quickly go over all the variables that we use in the formulation. And the first variable S represents a set of all stations in a bike sharing system. The second variable represents electric bikes that are present at a station I and time t, while the next variable Y represents the same information for regular bikes. The next variable I, superscript ME, represents the set of incoming trips that are of medium distance and have been taken using electric bikes. And the next variable represents the same information for regular bikes. And the next variable represents a set of outgoing medium distance trips that are taken using electric bike. And the last variable represents the same information for regular bikes. Having looked at the variables, here is the actual formulation. And the objective is to minimize the number of required electric bikes, the number of required regular bikes at the beginning of the time period over which we run our optimization for all stations from one to the last. And this is subject to these two main sets of constraints. The first set is demand constraints, and the other is flow conservation constraints. In demand constraints, we ensure that all incoming trips are satisfied by the number of bikes that are present at the station at the particular time of optimization. All outgoing trips are also satisfied by being equal to the sum of all outgoing long trips, all outgoing short trips, and all outgoing medium trips. The set of incoming trips added to the number of bikes currently present at the station should be greater or equal to all the outgoing trips, so that we ensure that all outgoing trips are satisfied. The set of incoming long trips and the set of incoming medium trips that are taken using an electric bike, and the set of the number of electric bikes present at the station at this time period t should be greater or equal to all the outgoing long trips that are leaving the station that should be taken using an electric bike, added to all the medium distance trips that are leaving the station also being taken by electric bikes. We represent the same constraint for regular bikes in the next equation. And we also ensure that all medium trips are a sum of all medium trips that are incoming while being taken by electric bikes and incoming while being taken by regular bikes. And the last equation here represents the same information for outgoing trips of medium distance. Flow conservation, we ensure that in the next time period, the number of electric bikes or the number of all bikes present in the stations, electric and regular, is equal to the number of bikes that were present at the station added to all the trips that came into the station at that time, and subtract all the trips that left that station at that time. So this ensures that we transition to the next time slot correctly. And the next two constraints ensure flow conservation for electric bikes using the long trips that came in, the median trips that came in while being taken by electric bikes, and the electric bikes that were present, subtract all the outgoing trips that utilized an electric bike. And the last information represents the same constraint for our regular bikes. This represents our formulation for trip substitution that ensures that all trip demand is met, including the substituted trips, and that we minimize the number of required bikes, while also ensuring that we take the correct bike for the correct type of trip, depending on whether the trip is long, short, or a medium distance. Now we apply our optimization formulation to our data sets, and here are some of the results. The first set of results we'll look at is the optimal number of bikes that are required to satisfy demand. And one observation we make here is that for a hybrid system that uses both types of bikes, we require a higher number of bikes. And this is because we want to ensure that the correct type of bike is taken for the correct type of trip. This is about 30% more than would be the case in a homogeneous system that was only using one type of bike. And this is because the constraint of taking the right bike for the right trip is no longer present, and we are therefore able to use a smaller number of bikes. The second graph, we see that doubling the number of trips that are substituted leads to only a 52% increase in the number of bikes, which is a sublinear increase with increased trip substitution. And this is an especially interesting observation because it shows us that with only a modest investment in the number of bikes, we can substitute even more taxi trips. In the last graph, we show that up to 6.6% of total carbon emission, which is about 2,100 metric tons, can be eliminated with only 10% trip substitution. Now, we also find that there exists opportunity to expand an existing bike share system while taking advantage of the latent demand that is formed by trip clusters that are currently outside of an existing bike sharing systems coverage. And to do so, we look at the location of bike stations in the city bike bike sharing system. And the red markers represent existing bike sharing bike stations. And you can see that they're mostly concentrated in the Manhattan region. And all the green markers represent taxi trips that are outside of 200 meters of any existing bike station. And on the right, we show, we apply a clustering algorithm. We use DBScan for our purpose. And the multicolored clusters represent areas of high trip density, taxi trip density, and this can form demand for new bike stations to be placed in these areas. And the black markers represent areas of sparse taxi trips which are not dense enough to form demand for a new bike station. Now, with this observation, we compute the number of stations that are required to be deployed in these areas to service this demand. And we apply our linear optimization framework again to these new areas. And here are some of the results. First, we find that we require about 1,760 stations in the expanded system compared to 941 in the current station, which is nearly double the number of stations. But this is a reasonable This is a reasonable observation since the geographical area covered by the expanded system is nearly 2 times the current coverage of the bike sharing system. We also find that we require about 33% more bikes, which again is an interesting observation because the number of bikes does not increase linearly with the number of stations. And finally, we show that the total annual CO2 emission can be reduced by up to 8% from such expansion and substitution. Now, our paper has a lot more results, and I encourage you to go read them. But in summary, we have shown that car rides are easily substitutable with bike ones, and this is due to the fact that most car trips are short, most of them being, or 50% of them being less than 3.6 kilometers, which is a bikeable distance. And also up to 70% of car rides are within 200 meters of an existing bike station, which means users can walk to the bike station as opposed to hailing a car. We also show that the number of bikes increases sublinearly with increased ride substitution. And this is an interesting observation because it shows that we only require a small investment to substitute even more car trips. We also show that there exists opportunity to expand an existing bike sharing system to areas that have no coverage by taking advantage of trip clusters that are outside of the current coverage area. And finally, we show that if implemented, ride substitution can lead to significant carbon reduction. Thank you very much for listening.